Hey, it's Chit from Kaizen Education. We're starting a video series where we go through assessment notifications for several schools, or schools in New South Wales, or even Queensland, since we have some students from Queensland. If you'd like us to break down your assessment and post it on YouTube, please send it to our email down below. All right, let's go through the Moorebank High School Year 12 Chemistry Assessment Task 1, Applications of Equilibrium and Chemical Equilibrium. All right, basic knowledge, basic things there. The task. This task involves the completion of three main components. Part A, chemical synthesis case study summary. Students have to research the application of chemical equilibrium systems in one of the following real-life applications: the Ostwald process, the Solvay process, the Frasch contact process. Students complete a summary of their case study in the table format. Part B is questioning and predicting the worksheet. Students explore one of the environmental, social, or economic issues for their case study in detail by completing the attached worksheet during class time. So interview session viva voce. There's going to be several minutes where you have to ask interview style questions. All right, so in order to undertake this task, you will need to research and summarize information about an industrial process from the options provided, summarize information into the table format, have a reference sheet, complete the attached worksheet, construct an appropriate research question, a hypothesis on one of the environmental, social, or economic issues for their chosen case study. Part C, prepare for your interview by practicing responses to questions in the question bank prior to the due date. Submit paper A and B. Okay, just general formatting there and reference guides. So part A, name of chosen chemical process, research the factors that need to be considered when considering your chemical synthesis process. Interesting. Okay, let me just edit my screen a bit. Awesome. So let's talk about the Ostwald process. Now, when you actually do your research, you'll find various different sources, and it's sometimes difficult to find sources with an accurate representation of the chemical equation. So you might see that in many of the images you find, these are all straight arrows. And rather than being equilibrium arrows, they're straight. But that isn't correct. And we know it from HSC chemistry that, if they're an equilibrium system, you have to write it as an equilibrium arrow. If it's not an equilibrium system, then it's fine to write it as a normal arrow, as we see here. And since this is from a past HSC question, I think this is probably a better version of the Ostwald process to talk about and use than the ones you might find online. So I encourage you to try and find examples of these from previous HSC papers. I'll try and see if I can put together some for this video series, but try your best to kind of look at the old syllabus, because the old syllabus, they had a lot of questions like this. They had a lot of different processes, and they had them all written out, and students had to go in and then know that system in detail and know how to describe it. So there's a lot of gold, per se, in the old syllabus, the old past papers, and the HSC marking guidelines for that. So you can find a lot of the answers to your response, to your assessment, in the answers to some of those old HSC papers. So those papers are between 2003 to 2018. But this is one that I pulled up from 2011. So the availability of reagents. Now, we have two reagents in the first step, ammonia and oxygen. Ammonia is relatively available. Ammonia is found in many different places, and ammonia is synthesized using the Haber process, which is a very cheap process where you combine nitrogen and hydrogen together. And everyone knows that nitrogen, there's 80% of all the air that we breathe is nitrogen. With hydrogen, we can easily get hydrogen from either electrolyzing water, or we can get hydrogen by removing it from a natural gas, such as methane. But just know that ammonia is very easy to Ammonia is very easy to access. You said that this is, you know, relatively available. And oxygen gas, that's also relatively available. I'd say this is easily and cheaply available. Especially because oxygen is from the atmosphere. Let's take a deep dive and look at the actual reaction conditions that have been prioritized in this system. Conditions of the reaction. Whenever I come across these equilibrium systems, I ask myself, what is the enthalpy? Is it an exothermic reaction? Is it an endothermic reaction? And how does the pressure affect the system? So I'd have to look at the number of gaseous moles and I'd have to look at the enthalpy. So having a look at the enthalpy here, we can see that it is an exothermic reaction. So exothermic means that heat is released. And to better conceptualize and understand it, I would actually put heat as one of my products. Since heat is being released, I'm going to put it as plus heat. Okay. All right. Let's talk about the temperature to start off with. Now, generally speaking, if you raise heat in this reaction, if you raise heat, it's going to cause the equilibrium position to shift that way, to use up the heat and do the reverse reaction. But yeah, that would bring down the yield. But they've chosen to use a very high temperature instead. So they've chosen to use 900 degrees Celsius. The reason being this maximizes the reaction rate. And as we all remember, increasing heat means that you increase the kinetic energy of the particles. And that leads to more successful collisions. Which leads to a greater reaction rate. So you have to talk about in step one that the reaction rate has been favored over the yield, over the equilibrium position. So you say that in step one, the reaction rates is favored and then 900 degrees Celsius, or the temperature that is 900 degrees Celsius, is a compromise. And this is to increase the amount of nitrous oxide produced and water produced as well. So that's the temperature, but there's also a gas aspect. There's a pressure aspect that we need to talk about. So I get rid of this stuff here. I have to ask myself how many gaseous moles there are on the left. So 4 plus 5, that's 9. 9 moles of gases. 4 plus 6, that's 10 moles of gases. So generally speaking, to maximize the yield, I'd have to have a lower pressure, but they've chosen to have a higher pressure or relatively high pressure. I wouldn't say it's incredibly high because it's 5 atmospheres, 5 times the pressure that we have in our atmosphere. And that would also increase the reaction rates. So 5 atmospheres is a higher pressure. And that means that the particles are in a smaller amount of space or a smaller volume, which means they're more likely to collide and then undergo successful collisions. This would increase reaction rate. So despite there being 9 moles on the left and 10 moles on the right, which would normally mean that you use a lower pressure, they've chosen to use a higher pressure to favor the increase in reaction rate for the first step. For the second step, they've chosen a slightly different approach. So the second step conditions reactions. Well, to maximize the yield in the next 2 steps, or to maximize the yield in step 2, they would use a slightly lower temperature or a relatively low temperature because delta H is negative because heat is a product. So if I lower the temperature, if I lower heat, it's going to want to shift to the right and then produce more heat. So that would increase the yield. So relatively low temperature to then increase my yield. Also, since there are 3 gaseous moles on this side and there's 2 on this side, it makes sense to have a much higher pressure. Because high pressure means that there's less volume. And it means it's going to favor the side with less gaseous moles. So those would be the most ideal conditions in step 2. For step 3, it's not an equilibrium system. So the only way for me to increase my reaction rate, to increase what I produce, would be to increase the temperature. Well, there's several ways. Increase the temperature, increase the reactants that I feed into it, and potentially increase the pressure as well, because that gives it a smaller amount of space, and that would generally shift it in the direction that it wants to go. So that's an outline of how you should approach this. As you do your research, you'll come across all the details for this. You want to list the temperature that each of the steps takes place in. So the temperature, the pressure for this step, and this step in your research. And you definitely want to use the word compromise somewhere, because all these reaction conditions are a compromise. There's not usually a way to have the perfect reaction conditions. If, let's say, for example, there's less gaseous moles on the right, then having an incredibly high pressure is going to shift it to the right. However, having a high pressure vessel means that there's going to be more maintenance, there's going to be more danger to staff. So there's a compromise pressure that's normally met. And in terms of yield and purity, you'll have to basically do your research and find the exact yield and purity for your process. But it should be It should depend on the conditions that they give you. And you might need to do some research on scientific papers to find that out. It's since it's nitric acid, since it's kind of involved in the production of a fertilizer, so used to produce fertilizer. What I would talk about is I would talk about how this addresses world hunger. So in to the increase in yes, the increase in the availability of HNO3 would mean that more fertilizer can generally be produced. This means more crops. That means that food becomes cheaper and more accessible, decreasing world hunger. Let's say if you wanted to talk about a positive impact that this can have, a positive social implication. Economic, I guess that also helps the economies produce more since you're using this as a way to produce a lot more crops. Environmental, you might want to talk about how the very high temperatures used require a lot of energy, and that's often from fossil fuels. And that fossil fuels are bad for the environment. Yeah, those are some of the ways you can take it. And you can also talk about kind of the effects of the release of HNO3 into water systems. Anyone that knows that HNO3 dissolves into nitrates might recall that nitrates actually are really bad for waterways. If you've ever seen the green sludge on top of waterways, that's because nitrates act as fertilizers for algae, and the algae would cover the surface of the water and then basically choke out the water from all its oxygen in a process known as eutrophication. So there was a lot about this in the old syllabus. If you want to dig through some of the past papers, then they'll have a lot of different things to say about each process and the effects that those processes have. If you want me to complete more of these, just let me know. If you'd like me to break down the rest of this, just let me know in the comments. And depending on how many people want a sequel video to this, I might, make another one.